In August of 2020, one of the auxiliary cables holding up the Arecibo radio telescope suffered a catastrophic failure and pulled out of its socket, causing widespread concern and damaging a portion of the dish below. Extensive reports by several agencies and companies were put forward to suggest methods of repairing or servicing the telescope in order to maintain its vital scientific operation. Unfortunately, they would not be given the chance. Built in 1960 to 1963, the Arecibo radio telescope was a colossal installation that housed a massive concrete dish to reflect radio waves and an intricate collector apparatus held up by 18 cables. It was historic in its ability to expand our knowledge of the universe, contributing significantly to radio astronomy, planetary radar observation, and most famously, the search for extraterrestrial life. It was the largest radar-capable telescope in the world and was responsible for numerous advancements in humanity's understanding of our place in the universe. But on December 1st, 2020, the entire cable system failed. Fortunately, though there were workers on site and nearby, nobody was injured. But the destruction of such an important monument to humanity's scientific discovery would have far-reaching consequences. The Arecibo radio telescope apparatus is held up by 3 sets of 6 cables named according to their position on a clock, 4, 8, and 12. The cables are comprised of steel wires with a complicated drying apparatus to slow the process of corrosion. These cables are held in place by Spelter sockets, which are made by splaying out the wires comprising each cable, pouring molten zinc into a mold, which then sets and allows the cable to be held in place securely. The first cable failure in August of 2020 raised significant alarm amongst the scientific community and prompted multiple reports that suggested many different ways of servicing and maintaining the telescope to ensure that it could remain active in the scientific community. Unfortunately, the proposed solutions would have come at a tremendous safety risk. As such, most engineering firms recommended demolishing the telescope carefully. However, they would not be given the chance, as just a few months later, the entire telescope array would collapse when another cable failed. As we will see in the following video, a single wire as part of one of the main cables snaps, which transfers significantly more stress onto the remaining cables and causes them to fail as well. That video was recorded by an Arecibo observatory drone operator monitoring the cables at the time. It shows the failure in very close detail from start to finish. The following video captures the failure from a much wider angle. The exact nature of the failure is explored extensively in a NASA report. This report identifies the main core of the failure being a cable pulling out of its Spelter socket, which caused further dynamic loading and resulted in the remaining cables also pulling out of their sockets. The NASA report reviews the design and features of the cable system, including these images of the overall structure, as well as the composition of individual cables. Each cable consists of 126 quarter-inch steel diameter wires wrapped around a single 7-wire strand in 6 concentric rings. Each individual wire has a specified minimum yield strength of 160 ksi, minimum ultimate tensile strength of 220 ksi, and elastic modulus of 23,000 ksi. The Spelter socket was comprised of a clevis-tang joint combined with an open socket type Spelter socket that held the individual wires, making up each cable in place by means of high-grade zinc. These figures show the microstructure of both the solidified zinc in the Spelter socket as well as the steel cables. The NASA report examines many causes of failure, among them corrosion, faulty design requirements such as factors of safety, and long-term stresses causing creep failure. The NASA report states that design criteria had a 1.83 factor of safety on rated braking strength without consideration for constituent stress margins. Loads predictions reviewed after the failure indicate up to 15% higher than design criteria and a less than 2.0 factor of safety. Additionally, the sustained dead load versus total load is significantly higher than for typical open socket terminations in bridges, hoists, etc. The NASA report also states that as the casting cooled and solidified, shrinkage occurred between the casting cap and the socket cone inner diameter, leaving a gap along the insides of the zinc casting nearest the casting cap. Additionally, 8 wire ends were found to touch the socket cone inner diameter, which provided a pathway for moisture intrusion. Additionally, this report notes that design verification lacked specific testing of creep, cyclic loading, and worst-case workmanship conditions. Credible failure modes were unqualified in the Arecibo Observatory application. The NASA report defines creep deformation as a time-dependent failure mechanism dependent on temperature and load. Over that time, creep deformation is divided into 3 stages: primary, secondary, and tertiary. In the primary stage, strain rate decreases with time and strain, which is due to strain hardening within the material. The secondary stage is characterized by the strain rate being relatively constant due to a balance of work hardening and annealing. This stage is typically the longest in duration, and no material strength is lost in this or the primary stage. In the tertiary stage, the strain rate increases exponentially, which is associated with the internal cracking or cavitation and decreases the effective material area. This process eventually leads to failure, termed creep rupture. It is my personal opinion that this creep failure was the primary cause of the overall Arecibo failure, which begs the question, what should we change for the future? NASA recommends in their report that further analysis should be conducted on the Arecibo sockets in order to better understand how Spelter sockets can fail, and more specifically, why some Spelter sockets in the Arecibo Observatory didn't fail and why others did. It is made clear from these notes from the NASA report that neglect in the design, as well as problems with the manufacturing, led to this disaster.